Good afternoon to all, and good night to my Portuguese fellow citizens. I propose to present a summary about my publications related to sequences whose elements are quaternions, differing from each other by the constitution of their terms. Okay, in this talk, I will present some special sequence whose terms are quaternions, defined by a recurrence relation, also presented, I'm going to present, as well as some properties of this sequence, the respective generating function, and also the generating matrix. Basically, I will present this kind of sequence that I have published. The first one that I will present, it will be h of x Fibonacci quaternion polynomials sequence. Then modify PEL and the modify kappa PEL quaternions and octonions. Also dual kappa PEL quaternions and octonions. Hyperbolic kappa PEL quaternion sequence. PEL, Lucas, kappa PEL and kappa PEL Lucas quaternions, unrestricted PEL and PEL Lucas quaternions, B-complex generalized Fibonacci quaternions, kappa PEL Lucas and modified kappa PEL Sedenions, and finally B-complex kappa PEL quaternions. In 2015, I have this paper, my first paper on this kind of sequence of quaternions. Here is the screen of the abstract of this paper. And also, as you can see, in this paper, I study this kind of quaternions sequence, which involve polynomials. And we present some properties of this sequence, as well as Binet style formula, ordinary generating function, and some identities. I present here the path followed to arrive at the sequence considered in this research paper. So we start with classical sequence of Fibonacci that everybody knows. Then we also consider the H Fibonacci polynomial sequence, and we have then the recurrence relation and initial conditions. Then we joint definition of quaternions in this kind of sequence, and we get a new sequence of quaternions, which the terms of these quaternions are exactly the h of x Fibonacci polynomials. And we have the definition of a term of order n of h of x Fibonacci quaternion, and also the recurrence relation that satisfies this sequence, and also the initial conditions. And then in this paper, we have the Binet formula, generating function, and some identities. Also, I present here only the results. The generating function of this kind of sequence has this aspect, this expression, and also we can get another expression for these generating functions. Also, if the polynomial is odd, we have another expression for generating function. And here in the theorem 3.6, we have the Binet formula. The Binet formula has when we have the Binet formula, we have the opportunity to find the term of any order in terms of the roots of characteristic equation. In 2016, we have 3 more papers about this sequence that I mentioned before. The first one, it was in modify PEL and modify kappa PEL quaternions and octonions. Second one, it was again with the first sequence that I have published in 2015. It was now the difference is because I consider some types of matrices whose entries are exactly elements of this sequence. And the third paper, it was about some combinatorial properties of the first sequence that I have presented here. We have, as I have before, I have the screen of the abstract of the first paper, and also the path that I followed to find this sequence, to arrive to this sequence, at this sequence. So we consider the modified Pell sequence, which has this recurrence relation. Then we consider a generalized sequence of modified Pell, and we introduce some integer k in the recurrence relation, using again the definition of quaternions and octonions, and we get this sequence of quaternions and octonions that I have studied in this research paper. Also, the binary formula and generating functions and some properties I have in this research. Here is the generating function of this sequence, and also the binary formula of this sequence of quaternions. In this case, involve, of course, more quaternions of alpha 1 and alpha 2, given by these equalities here. Here we have some properties of this sequence, like some identities, the Catalan's identity, for example, also the norms of these quaternions, the square of the norms, and also more identities of this sequence. The second one is Cassini identities, and the other one the Dodekaine identity. Also, in this, you have the generating function of this sequence and the binary formula as well. Okay, the same. For the next one, the second, have also the abstract of this paper, and in this paper I use some matrices, some types of matrices whose entries are exactly elements of this sequence. For this, we use the R circular matrices, and if you put in the entries of this matrix elements of this sequence, we can prove that the determinant of this kind of matrices is given by this expression with quaternions. Also, if you use left circular matrices, also the determinant of this kind of sequence whose entries are elements of this sequence is given by this expression, the determinant. Also, if you consider, have here the definition of G circulant matrices, and if you put the entries, if you consider the entries of this matrix elements of this sequence, also the determinant of this kind of matrices is given by this expression involving the quaternions. Using this type of tridiagonal matrices, where the other entries are nulls, and in the diagonal, principal diagonal, we have this kind of elements, we can show that the determinant of this kind of sequence is exactly the terms of order n+1 of this sequence. of quaternions. Also in the proposition 4.3, also the terms of order n of this sequence can be given by the determinant of this type of three-diagonal matrices. In a third paper about some combinatorial properties of this sequence, we study some, of course, like we have in the abstract, we present some properties involving these polynomials, including the exponential and Poisson generating functions. We have here some their combinatorial properties. Here, the sum of the n first terms of this sequence is given by this expression, and also this combinatorial property. Again, we have the exponential generating function is given by the first expression that I have in theorem 3.1, and also for as a corollary of this, of course, we have the Poisson generating function of this kind of sequences. In 2017, I and one colleague of my university, we decided to join the definition of dual numbers and consider a new sequence using the dual numbers. And we have here the sequence of dual kappa-Pell quaternions and octonions. Also, we have studied also some properties and the generating functions, and also linear formula and some identities of this sequence using now the dual part of this. So we start with the kappa-Pell sequence, the modified kappa-Pell sequence, the kappa-Pell-Lucas sequence, and we use the definition of dual numbers and also the definition of quaternions and octonions. We joined all together and we construct a new sequence of quaternions, and we call this sequence dual kappa-Pell. We have three kinds of sequence here: dual kappa-Pell, dual kappa-Pell-Lucas, and dual modified kappa-Pell numbers, sequence of quaternions and octonions. In this paper, we have the definition, because we involved the dual number, we have the definition on the left side, the definition of dual kappa-Pell, Lucas, and the modified kappa-Pell quaternions, and some properties on the right side, and also the definition of quaternions both. On this slide, we can see the generating function of each other and also the linear formula of each other. Also here we have some definition, the definition of dual kappa-Pell, Lucas, and modified kappa-Pell octonions, which is an extension of quaternions, as we said before. But we study also octonions here in the last section of the paper, only a brief section. And we have also the generating functions and also the linear formula for three of kinds of this sequence of octonions. In 2008, we decided to introduce a new sequence of quaternions, and we decided to use the hyperbolic case. And we have the first paper, it was on hyperbolic kappa-Pell quaternion sequences. The second one, we decided to introduce matrices in this kind of sequence that we studied before. And a third, me and a colleague of Turkish, we decided to introduce a new kind of sequence, which is called by unrestricted Pell and Pell-Lucas quaternions. About hyperbolic kappa-Pell quaternions, we have also the abstract and the front page of the paper, and also the path that we followed to arrive at this sequence. again, we use the definition of dual numbers, the definition of quaternions and octonions, and the hyperbolic functions also here. Here is the definition of hyperbolic functions, only to recall. And the hyperbolic kappa-pel sin and hyperbolic kappa-pel cosine quaternions are defined this way. So the generating function of hyperbolic kappa-pel quaternion sequence are given by this expression here for sin and cosine. And the Binet formula for sin and cosine is also given by this expression, where A and B are this quaternion here defined. And the second paper on the matrices about the other sequence of quaternions that you have mentioned before, some types here, the work with the Turkish colleague about the unrestricted Pell and Pell-Lucas quaternions. In 2019, I have 3 papers about the B-complex generalized Fibonacci quaternions with another colleague from Turkish, and also a sequence of B-complex kappa-Pel quaternions and kappa-Pel, kappa-Pel-Lucas, and modified kappa-Pel sedenions in these journals. On the B-complex generalized Fibonacci quaternions, it was a work with a colleague or with 2 colleagues from Turkish, and we have in this paper introduced the B-complex generalized Fibonacci quaternions. Also, we give the Binet formula, generating function, and some summation formula for this type of quaternions are also given in this paper. And lastly, as we said in the abstract, as an application represents the determinant of a special matrices, and we show that the determinant is equal to the term of order n of the B-complex generalized Fibonacci quaternions. The difference here is, the path is this here. We start with B-complex numbers. We introduced, we joined the definition of quaternions, Fibonacci and Lucas quaternions, generalized Fibonacci sequence. Also, then B-complex generalized Fibonacci sequence, then B-complex generalized Fibonacci quaternion sequence, and about this last one sequence, we give the Binet formula, generating functions, and some properties. Here, we recall what is a B-complex numbers, okay? There is no problem. And what is a generalized Fibonacci sequence? Here we have a recurrence relation of order 3. The other sequence, the recurrence relations are of order 2. Then B-complex generalized Fibonacci quaternion is defined by this. What I have here in this screen with initial condition given by this expression here. And the generating function is given by this expression here for this kind of B-complex generalized Fibonacci quaternion sequence. And the Binet formula of this kind of sequence is given by this expression here. We have some sketch here of the proof of this result, the Binet formula of this kind of sequence. And also we have the exponential generating function of this B-complex generalized Fibonacci quaternions is given by this expression. And also we have here the proof of this theorem. In 2019, also, I published about B-complex kappa-Pel quaternions. I don't have time to give all these things here. And also the Kappa-Pel, Lucas, and modified Kappa-Pel sedenions in this journal. Before I start, I would like to say that this is what I prepared to show you. Due to the limited presentation time, it was not possible for me to spend more time with the more detailed presentations of these topics. However, I hope I have met the objectives of which I had set myself. Thank you very much for your attention.
Thank you.
That was actually very good, because I think most of us end up doing overviews, because I certainly didn't go into a lot of details about what I did, and I don't think anyone else has. All right.
Yeah,
So thank you very much. Any questions about what she just discussed?
Well, I'll just note, thank you for an excellent presentation. So my quick thought is, are there any, so these sequences, these quaternion sequences that you generate, are there any kind of geometric realizations of these sequences? And do they have, you know, are there any sort of some consequential geometric realizations of these sequences of quaternions that you've described?
Okay, I didn't think about this now, but of course there is a relation with geometric parts of this kind of sequence. This is good for the future.
Okay, thanks.
Well, to answer your question, Terence, using octonions, for example, octonions multiply in a special way, like octonionic coefficients EI, EJ gives you minus delta Rj plus I epsilon Rjk type of a thing. And you can extend it into from quaternions into octonions in a nice way, and you have this octonionic multiplication tables. And they only are able to show you like in doublets of octonions, but we produced some, I think maybe around 10 years ago, under my name and maybe with Česmer Burdek, Burdik, from Prague, some geometries that you just asked about. So in other words, if you have two arbitrary lines and you put like octonionic numbers on one and others on the other, and you crisscross them and they give you like the Pappus's theorem, other octonionic numbers in between. But what they do is they map all these geometries, like Pappus's geometry, the Sagues's geometry, and so on, all onto each other in a very beautiful way.
Yeah.
So you could see that paper in the old papers that we wrote. That might help you to answer your question a little bit.
Thank you.
Which paper is that again?
The paper was published, I think, in a colloquium in Prague. Okay. On the colloquia they usually run every year. But I should tell you guys that I'm on the international committees of a bunch of colloquia. There's going to be a group theory meeting, if everything is okay, next year in Africa, in Benin.
Oh, wow.
If anybody wants to come there, let me know, so that I'm on the international advisory committee, so I can put your name in there as a speaker.
Oh, thank you.
Thank you.
Thank you.
You're welcome. And then also in Prague and also in Ukraine, there's going to be a bunch of meetings, and also in Russia. It's outside of Moscow. Okay.
I know that the ICM, the next one, is actually going to be in St. Petersburg.
Right. Yeah, I'm talking about physics conferences.
Yeah, I know, but I was mentioning about the ICM for those of you, for those of math conferences, but even though, I mean, etc.
Yeah,
Can I say one thing more?
Yes,
I would like to give the opportunity to inform you that in this year we are thinking to organize in my university, which is in Portugal, of course, in Vila Real, Universidade de Trás-os-Montes e Alto Douro. We will organize the new trends on quaternions and octonions. The next version it was in my university in November or December of this year.
That's great.
Okay.
Paula, you
Oh,
were
that's-
from Turkey. The greatest Turkish scientist was my advisor, Feza Gürsey. Gürsey.
Can you give me the name and send me?
Yeah, Gürsey was the person who introduced octonions and the quaternions into physics for the first time, basically. Not quaternions, but octonions. And building all the G2F4, E6, E7, E8 groups, and then they led into superunification, grand unified theories, and everything else. So, but Feza Gürsey is the name, and is probably the only greatest scientist Turks ever produced.
Okay. Thank you.
Okay.
Thank you very much. That was a nice talk.
Yeah, it was
That
a
was
nice
a nice
talk.
Can I ask just a crazy question? How did you, where did you start doing that? When when I looked at it, it just seemed so natural, but I've never thought of the work that you were doing before. Sequences of quaternions, and in particular, kind of tracking them along, like the Fibonacci sequence and so on. What are the sort of like early roots of that?
I decided to start to work in a sequence of quaternions because before I had papers about the sequence of numbers, integers.
Yes.
And but now also I am interested in study another kind of sequence, not a sequence of integers, but also sequence of rational numbers. I enjoy to work in this kind of sequence. Now I am interested in the check where this can be applied in applied mathematics or something, because I think that it will be applied in some.
Well, Paula, it will be great to go to Portugal because well, I'm reading Pessoa all the time, but I've been hanging out in the fado joints in Portugal like all night long. It's a great place. Great place for Portuguese music is beautiful. Yeah. So anyway, everybody should be invited there.
Oh yes, it sounds wonderful. I mean, the pictures were beautiful. Yeah, I saw those pictures.
It is. Yeah.
Absolutely. Oh man. I want this pandemic to be over. I want to travel again. Over.
Right. Well, from Amalia Rodriguez to Luis Bonfa to all the new fado people. It's
exactly.
Just a beautiful language and great
right.
country. Yeah.
That's where Rodriguez's family was originally from. That's his lineage. Exactly.
Right.
Portugal. Rodriguez is spelled the Portuguese way, not the Spanish way.
Right.
Great. So thank you so much. So I wish to thank the organizers for inviting me to this session. So you already mentioned the title of my talk, Reproducing kernel spaces in hypercomplex analysis. And really the talk will be divided into two parts. The first part will be more classical. I would like to review a number of facts on reproducing kernel spaces and some basic concepts. And in the second part, and some reproducing kernel spaces which play an important role. And then to see some of their counterparts, so outline their counterparts in the setting of quaternions, split quaternions, and also some other topic maybe. So as I mentioned, I would like to mention a bit, I will discuss some definitions, and then the Bergman-Fock-Siegel space, Druria-Verson space, and the Debranche-Rovniak spaces, some definitions. And then we'll see in the setting of Water series for and quaternions and split quaternions. I would like to mention there are very important cases I will not touch upon, of course, in this talk, like the Grassmann algebra, Clifford algebra, polyslice analytic functions, ternary algebra, bicomplex numbers, and so on. But I will give some references at the end of the talk. So maybe let me begin by the definition of a reproducing kernel Hilbert space. Let me begin by the definition of a reproducing kernel Hilbert space. So it is a Hilbert space of functions. So that in particular excludes spaces like the Lebesgue space, for which the point evaluations are bounded. And by Riesz theorem, so the point evaluation is represented by an inner product. And so the inner product KZ is called the reproducing kernel. And the reproducing kernel, and so that would be true also for reproducing kernel quaternionic spaces, of course. So these three, the first part can be quaternionic or complex. It will not make much difference. The reproducing kernel is positive definite. The terminology is misleading, but this is the accepted terminology, but there is nothing definite here. It's just positive or non-negative, in the sense that all these sums are non-negative, and this is just a computation of some norm. Now, if you rewrite this sum as a matrix, you see that all these matrices are non-negative. Now, by the way, you can also ask that all these matrices have at most kappa, where kappa is fixed, a fixed number of strictly negative eigenvalues. And then you speak about Pontryagin eigenspaces, which would be a direct sum of a Hilbert space and a finite dimensional Hilbert space with a minus with inner products. And also this also makes sense for in the quaternionic setting, since the spectral theorem holds for Hermitian quaternionic matrices. I would like to mention that machine learning was mentioned this morning, and functions with negative squares, so not only positive definite functions, also appear recently in machine learning, interestingly. So this notion makes sense also in the quaternionic setting. And there is a one-to-one correspondence between positive definite functions and reproducing kernel Hilbert spaces. And you can extend it to functions of negative squares and reproducing kernel Pontryagin eigenspaces. Now, if you want a difference of a direct sum of two Hilbert spaces with a minus with a sum, you have Krein spaces, and then the situation is more complicated. And Laurent Schwartz of distribution fame, Laurent Schwartz proved in '64 that there is an onto but not one-to-one correspondence between difference of positive definite functions and reproducing kernel Krein spaces. Another definition which would be important is that the notion of factorizable function is, if you can write it like what is here on the board, HW, HZ, where capital H is a Hilbert space, or if you want a pre-Hilbert space, and the function is factorizable if and only if it's positive definite. So that's a good. So it's not always easy to see, and or I would like also to mention the connection with stochastic processes, which is very important. I mean, positive definite functions are have an important application in the theory of stochastic processes. And it's not always easy to see the function is positive definite. I mean, an example I like in particular is this one. I mean, is it positive definite? It seems impossible to check. But if you see this formula, well, it is in fact a sum of two factorizable functions, so it's positive definite. Now, this formula, it seems to come out of the blue, but in fact, it is a special case of a general formula for stochastic processes with stationary increments, and then it's quite natural. And it is in fact the covariance function of a fractional Brownian motion, and H is called the Earth parameter. And so that's an interesting point of this kind of formula. So I would like to mention also that not every Hilbert space is a reproducing of functions. I mean, is a reproducing kernel Hilbert space. To have counterexamples, you need the axiom of choice and the fact that a vector basis in a Hilbert space is uncountable. I will not mention here this result of Donegal-Mazzani, but it's quite interesting. So before I go to the quaternionic setting, I would like to mention three spaces. On the first Bergman-Fock-Segall, I will say a few. I mean, I have 3 slides. The 2 other spaces, I will speak more succinctly, and then we'll see counterparts of these in the quaternionic setting. The Bergman-Fock-Segall space. So this is a space of entire functions with this integral to be finite. So this is kind of a geometric description, if you want. The point evaluations are bounded. And this is a reproducing kernel. More interestingly, maybe, you see that the polynomials belong to the space, and they're orthogonal, not orthonormal. And so you can characterize in terms of the Taylor series at the origin by this sum here that you see, this sum to be finite with the factors factorial n. And the Fock space can be also characterized as a unique space of entire functions up to some multiplicative factor, where the adjoint of differentiation is multiplication, and the motivation is from quantum mechanics. And two more words, that you have this map here, which is called the Bergman transform, which is unitary from L2 into the Fock space. Why do I mention all this? And you are here the connection between position operator and momentum operator in the L2 setting in quantum mechanics and their image in the Fock space. Why am I mentioning all this? Because it gives you kind of a roadmap when you want to study a reproducing kernel Hilbert space, be it in the quaternionic setting or in the Hilbert space, the classical setting. So what you have a Hilbert space of functions. The point evaluations are bounded, so you have a reproducing kernel, but that's not enough. So what is interesting is to see in general if you have a geometric or analytic representation characterization. Here we have two of them, sometimes you don't have one. Here we have an important motivation from quantum mechanics, and I would like to mention also the Bergman transform suggests, I mean, it has been studied applications also to signal processing, because you transform a function in L2, which has very bad properties, into an entire function. So it allows very nice applications, and it can be characterized in terms of a function. So this is kind of a roadmap. I do not claim that every Hilbert space you can answer all these questions, and I do not claim either that there are not other questions which are not important, which I didn't mention here, but this is still kind of questions which are important to answer, I would say. So this is the Bergman-Fock-Seagal space. It's an important space. You see, it bears three names, so one can imagine it's quite important. The Drury-Averson space is also very important, but I will give it. We will meet it later in the setting of Fouetter's series. So we're now in several complex variables. We have a unit ball of Cn. This is a positive definite kernel. The corresponding space is called the Drury-Averson space. And why is it important? Because of von Neumann inequality for row contractions, which I write here. If you have commuting operators in a Hilbert space, such that the row is a contraction, then you have this inequality. So you see on the right here, you don't see the AN and not the original space. All this is a uniform bond in some sense. In a quaternionic setting, we can see a proof of a corresponding result in a paper with Kaptanoglu in CVEE. So this is a second example I wanted to mention. And once over the aim of this first part, it will give a kind of a small survey of what kind of interesting problems one can see after that in the quaternionic setting. And there are counterparts of a Drury-Averson space in the quaternionic setting, as we'll say. And the other example is related to the Branch-Rovniak spaces. So this is a huge domain. I will mention only one example and very, very quickly. But the best way to introduce them is really to go back to the Berlin invariant subspaces. You have here the RD space. We have in a previous talk, there were polynomials in Q. We'll meet also such infinite series, in fact, in the quaternionic variable Q a bit later. But here, this is in the variable Z. So this is the RD space. And Berling's theorem characterizes the closed invariant subspace of this RD space under multiplication by Z. And these are really the JH2, where J is inner. Inner meaning that it has contractive in the open unit disk and boundary value equal to 1 on the boundary. And this is a reproducing kernel. And if you replace J by a function which now will be analytic and contractive in the open unit disk, you get the Branch-Rovniak space, and everything is now contractively included, and not it's not an isometric inclusion. And we'll meet this. So here we have seen three spaces really. Let me just repeat: the Branch-Rovniak spaces, which will be with this reproducing kernel. They appear, if you want, in inner system theory, in invariant subspace theory, in interpolation. The Drury-Averson space, which appears more in operator theory in several complex variables for several operators. And if I backtrack once more, we had the Fock space, which appears mainly, let's say, in quantum mechanics. Now I would like to see some counterparts in the, allow me to, in the quaternionic setting. So I'm not so sure I have to introduce here the field of quaternions, a skew field of quaternions. So, well, I was educated in France, as you can hear from the accent, and there it's a field, it's commutative, we say commutative field and field, not, I mean, it's a bit different from here, but here, so the skew field, the anti-commutative, it's not commutative, this is the definition, but we'll meet it later. And here we have also the split quaternions, which are not a field, this is a multiplication table. It's a bit difficult to see what it is, but the next slide will show it in a better way, because we have here the construction, let's say if you want, of the quaternions and of the split quaternions. So the quaternions, you can view them as matrices with complex entries, Z1, Z2, minus Z2 bar, Z1 bar, and it's and split quaternion, you can view them without the minus here. And the lack of this minus will create very interesting situations I will explain. So this is stable also. If this is invertible, this is stable under inversion, but there are a lot of matrices like this which are not invertible. Of course, you just have to have a module of Z1 equal to the modulus of Z2, and here all the matrices which are different from zero will be invertible. So so these are the quaternions and split quaternions. Now, when you want to go to the hypercomplex setting in the problems I wanted to explain here, you need the notion of positivity. As I mentioned already, in the quaternionic setting, it is not really a problem because you have the spectral theorem for Hermitian matrices. But there is also this map. Here, A and B are matrices with complex entries, but and it allows you to transfer the problems from quaternions or matrices with quaternionic entries to matrices with complex entries. And in a split quaternionic setting, you have this one. And here there is something interesting for the split quaternion. You have two natural adjoints. This doesn't appear for this one. You can just take the adjoint, and it corresponds to here a natural symmetry. Or you can take this one, where J0 is 1, 0, 0, minus 1. And here you have another, so this one is not a split quaternion, this J0. But when you make the whole product, it goes back to be a split quaternion, and it gives another symmetry, in some sense, an indefinite inner product in the coefficient space, and that leads to reproducing kernel crime spaces. Now, so I would like to show some spaces. So we have a Cauchy-Fouetter operator here, and if you have, if you define these, so let's call hyperanalytic functions which are in its kernel. If you define d bar like this, you will notice that dd bar factorizes the Laplacian in R4 in the same sense that this classical operator factorizes the Laplacian in R2. Now, if I would like also to mention that if you identify H with C2, you get pairs of Cauchy-Riemann equations, but they will not play a role here. Now, the product, it was also mentioned in the previous talk, really, the product of two hyperanalytic functions is not hyperanalytic, and the quaternionic variable is not hyperanalytic. So that's quite negative things. On the other hand, you have here these variables, which are called the Fouetter variables, which are hyperanalytic, and which were introduced by Fouetter, and which are in some sense the building block of hyperanalytic functions. And I would like to, they were introduced by Fouetter in 36. In the next slide, I would like to explain how they can be introduced in a different way. And that's a work which was done with Shapiro and Volock some time ago. So you take an hyperanalytic function, you differentiate, and then you replace the differentiation with respect to x0 by this, because the whole sum is 0. And then you get this equation in a very natural way. You see that you have here the Fouetter variables. Then when you integrate back, you get this, and you have in a natural way, if you iterate, you have a Fouetter series, which were introduced by Fouetter in the 30s. I would like to mention that the same method works also for split quaternions and ternary algebras. And there is a general approach which was developed with my student Ismail Paiva and with Daniel Strupa, which appeared recently in the Israel Journal of Math, which can include all these kind of variables. But basically, if you want, in this setting, the Zn of in several complex variable is replaced by this symmetrized product. There is a product, it's not the pointwise product, it is a Cauchy-Kovalevskaya product. It's a convolution on the coefficients, and it's called Cauchy-Kovalevskaya because in some other definition, it uses Cauchy-Kovalevskaya extension problems from extension theorem, from PDEs. I promise the quaternion inversion space. So now let me to backtrack. Basically, the trade secret is that each time you replace Zn by zeta alpha, it's a bit more complicated, but this is what is behind. And here you have a quaternionic inversion space, and we can characterize it in terms of power series. And it has the same structure theorem, structure properties than in the classical case. So this shows really, I mean, this shows really that this zeta alpha really play the role of the monomials in several complex variables. So here we have one. So this is for the Fouetter series. So let me backtrack here. I would like to mention once more. In this case, we're in the kernel of this Cauchy-Fouetter operator. Now there are also in this series, in this setting, we have also the Branch-Rovniak spaces. Now we're in a non-commutative setting. So the formula which I gave before, like 1 minus S star divided by 1 minus Z omega bar, it doesn't work anymore. And you have to write the thing. I mean, you can express it in terms of a multiplication operator. And then you have this kind of expression, which is the non-commutative version. You see, you cannot write S of Z, zeta nu of X, because it's not pointwise. You cannot do it pointwise. But you can look at the multiplication operator and evaluate. You have also Blaschke factors. I mean, you have so you can go the whole way there. It works also for split quaternions. So the split quaternions, there are some other difficulties. So that would be the operator corresponding, and you have a factorization of the ultra hyperbolic wave operator. Now the solutions need not be smooth and real analytic, but we will focus on the real analytic solutions of this equation. And you have, I will not write too many details, but you have the same, you have here the same characterization, and you have new variables here. I mean, these are the Fouetter variables, Fouetter type variables. And as I said, with Paiva and Strupa, we have a general setting where in every case we have different kind of Fouetter type variables. So, and the proof is the same, so I will not go over it. Now, I would like to, so the next topic is related really to the previous talk, because these are slice hyperholomorphic functions. So when you look at the quaternionic variable Q, it's not hyperholomorphic, so that's really a kind of a problem, but it is slice hyperholomorphic, which was a notion introduced by Colombo, Savani, Strupa, and Giloni and Strupa, and it means really that you identify H with C2 each time along a different unit, square root of identity, and you want the function to be analytic along all the planes. And then, so the quaternionic variable is analytic, the power series analytic, the pointwise product is not analytic, so it goes back, but, and the convolution on the coefficients is slice hyperholomorphic. The next slides are just for a pointer. I don't want to spend too much time in it, but just to say that the notion of spectrum here is more difficult to introduce for matrices, but you have a notion of S spectrum, which really fits to this to this setting. And really you see that it corresponds here that this kind of power series can be expressed in terms of this kind of generalized resolvent. So here, this is easier, you see, because here the coefficients are real. So you have a function with quaternionic coefficients, but here this polynomial equation is with real coefficients. This kind of expression also appears at around the same time in a paper with Rodman and Ran, I should say. Now we have here the RD space, and you can define the branch-Rovniak space in the same way in terms of power series, in terms of multiplication operator, and in terms of power series. So there would be much more to say, but the point I wanted to mention really is that you have a very important notion of opposing spaces in analysis, let's say, and in other topics. And when you go to various different sets of constants, if I may say, then you can define also such spaces. But you have a main difficulty quite often. The main difficulty is that you cannot define a pointwise product. And in fact, in all the time I'm aware of, the pointwise product is replaced by the convolution on the coefficients, which goes back at the end of the day also to the work of Michel Fliess on non-commutative series. That will be the end of my talk. Let me give some references, quick references. My slides are available, so I will not go all over it. So here's just 3 books. So this is really for the size hyperhomomorphic setting. This is for bicomplex case, which I didn't mention. And since Portugal was mentioned a couple of times, so I would like to mention in particular my colleagues from Portugal, Paula Cerejeras and Uwe Keller, and this paper which will appear soon. And I wish to thank you for your attention, and this is really what I wanted to say. Thank you.
Thank you.
Thank you very, very much. Any questions? Does anybody have any questions?
So I could just ask one. I mean, so I get the sense of the challenge is kind of reproducing these kernel spaces in the sort of quaternion and the split quaternion setup and beyond. And what I'm missing is sort of you just started to allude to it about the sort of pointwise product. Can you just say that once more again, the obstruction that you're overcoming?
Yes, if that was, in fact, you take, let's say let me go back for, well, let's say you have a slice hyperhomomorphic function. So they're allomorphic in every slice. But if you take, let's say if you had, so Q times Q, if I call Q the power series, the variable Q times Q will still have this property. But suppose you take A and B to quaternions, QA times QB will not be. But Q square times AB will be. That will be the convolution. I mean, you put all the scalars at the end.
I see.
And that would be the same for the polynomials which you mentioned in the previous talk. You see, this is a kind of same.
This is a sort of philosophy for doing this.
Yes, yeah.
I see.
And it's when you trace, I mean, people found this independently, this kind of product, but it goes back to the theory of non-commutative series, and you see that you cannot commute, so you play only on the coefficient.
I see.
I'm sorry you cannot see me, but my camera, I mean, I'm looking on my computer.
Actually, we can see you.
I see you fine.
You have a little picture over here with a nice background.
You have a wonderful background behind you. And
yeah. Where are you? Where's your background?
This is in, no, I mean at home in Irvine, but this is Paris in the background.
Oh, it looks really, really romantic. Okay.
Yeah.
Where are you from, by the way?
Well, I'm a complicated story, but I'm from France, but I've lived a very long time in Israel.
Ah.
In Spain, yeah.
Yeah, I noticed the accent. I said, he sounds French. And
Yeah,
I'm saying to myself, this man sounds French, but you know, the last name doesn't strike me as a French name, but he sounds very French.
So thank you very much for inviting me at this session. I want to just
we're
say
very
once
happy
more.
to have you. Thank you for attending.
excellent talk. Okay, colleagues, using quaternions to prove theorems in spherical geometry, Marshall Whittlesey from Cal State University, San Marcos.
All right, thank you for the invitation to speak. Can you see my slides all right?
You can see them perfectly.
All right. Oh, there we go. So I'm going to show how to use quaternions to prove a curious theorem that's well known in spherical geometry, but probably not well known to people outside of spherical geometry. So let me describe how I get to it. So what I've done in this first slide here is construct a spherical right triangle ABC. So I'm drawing on a sphere. The sides of a spherical right triangle are great circle arcs. So I have 3 points A, B, and C, and the great circle arc in between each one of them. And there's a right angle at C. The sides have measures. The measures are the measures of the arcs. All right, so if you have the center of the sphere over here, then the measure of the arc is the measure of the central angle. Okay, and so the so-called spherical Pythagorean theorem says that if you have degree or radian measures for each of the arcs in a right triangle, then the cosine of the measure of the hypotenuse is the product of the cosine of one leg times the cosine of the other leg. So that I mentioned in an aside is another fun theorem to prove with quaternions, and I actually did that at the last quaternion section, but I will just take it for granted today and use it to do something else. All right, so start with this spherical right triangle ABC, and what I'm going to do in this diagram is show how to generate more theorems about the relationships between sides and angles in a spherical right triangle. And the way we do that is that we extend AC over to E and extend AB out to D. By the way, can you see where I'm pointing with my mouse?
Yes, we can.
Yes, we can.
Yes. Okay, just wanted to make sure. Okay, so you extend AC out to E and AB out to D so that AD and AE are quarter circle arcs, so they each have measure pi halves. And then I connect E through D with an arc and extend through that to the point that it meets the arc BC extended at point F. Okay, so what you can kind of see here is I started out with a right triangle, and I have in AC kind of a base, an equator, and having constructed now at A, C, and E 3 vertical perpendiculars, they now meet at the North Pole, F, the so-called pole of the base great circle passing through A, C, and E. Okay, and I then focus on the spherical right triangle that I created above it, BDF. I can calculate the measures rather easily of all of its sides and angles. If I started out with this hypotenuse AB and extended it to have a measure of pi halves, then what's left, of course, is pi halves minus C. Same thing down here, B, if I extend it to be pi halves, then what's left here is pi halves minus B. If I start out here with angle B, then there's a vertical angle here up. This measure of this is angle B as well. And extending CB up to the North Pole at F, I started out with A, and if I extend it up to be a quarter circle, then what's left is pi halves minus A, etc. A couple of details that are not perhaps not quite so obvious are, first of all, if at angle A over here, angle BAC, if it has measure A, then whenever you have on a great circle from a point, if you extend out 2 arcs, with both being a quarter circle and plot their endpoints, then the measure of the arc between those 2 endpoints is the measure of the angle at A. Okay, the idea, it's exactly the idea that when you would start out with the North Pole and you extend 2 quarter circles down to the equator, then the difference in longitude between the two meridians that you have there can be seen in two ways, either the angle between the two curves at the North Pole or the distance between the point on the equator where those two meridians meet. Okay, so that's a helpful correspondence between angles and arc measure in spherical geometry. All right, so the angle here, measure A, becomes the measure of this arc, DE, and since that's being extended up to the North Pole, this becomes pi halves minus A, etc. So we get all the sides and angles of this triangle BDF up here. And since it's a spherical right triangle, we can apply the spherical Pythagorean theorem to it. All right, so the cosine of BF equals the cosine of FD times the cosine of DB. All right, and I have the measures of each of these. Each of these has been calculated in terms of the original A, B, C sides and angles of the original right triangle. And so cosine pi halves minus A is cosine pi halves minus C times cosine pi halves minus capital A. And then using basic trigonometry, of course, cosine pi halves minus anything is the sine of each of those. And so we get a statement about relating sine little a, sine little c, and sine capital A. And that is a theorem about what's going on in the original triangle, ABC. Okay, and in fact, it tells you how to calculate in a spherical right triangle the sine of the measure of a particular angle in terms of two sides, the opposite side A and the hypotenuse C. And the sine of A is the sine of opposite over the sine of the hypotenuse. Okay, so this is an important theorem generating machine and standard trick in spherical trigonometry. Okay, any statement now that I have about a spherical right triangle, if I apply it to this triangle BDF up here, which is called the complemental triangle, by the way, because of all these complements that I have flying around. All right, if I apply that theorem to the complemental triangle, it becomes a statement about the sides and angles of the original triangle. All right, so here I took the spherical Pythagorean theorem and produced another one. All right, now the thing is, what I can do with this is produce more theorems by doing this whole process again. Okay, I started out with ABC, created the complemental triangle by extending CB past B and AB past B out to D, F, and B. Well, now with the complemental triangle, create the complemental triangle of that. Okay, so you would do that by extending BD. I didn't draw all the details here, but you would extend BD, extend BF, so that out to G, so that BG has a quarter circle. Extend BD out to be a quarter circle, connect it through G up to H, and you get a third triangle, which I call the second complemental triangle, although there's no accepted name for it, really. All right, and once again, you can calculate the sides and angles of that and apply the Pythagorean theorem to that. All right, its hypotenuse turns out to have measure capital A, which was the measure of the angle A in the original triangle. And we have the other two sides as well. And I get cosine hypotenuse equals product of the cosine of the legs. Cosine pi halves minus anything is the sine. And so now I get a statement for the original triangle relating the sine of the angle B, the cosine of the angle A, and the cosine of one of the legs. Okay, and this is, again, another important result in spherical right triangles. All right, well, I'm sure you can't guess what I'm going to do next. Do it again. All right, start with this triangle, create the complemental triangle of that, calculate the sides and measures of that triangle, apply the Pythagorean theorem to that, and get another statement relating the sides and measures of the angles of the original triangle. And then after that, what would I do next? Do it again, okay? So the question is, every time I do this, I'm getting a new theorem on the original triangle, almost for free. Can I keep this up forever? I mean, how long does this go on? I mean, am I going to create infinitely many theorems just by creating complemental triangle after complemental triangle? Well, the answer is no. All right, and in fact, the game ends after doing it 5 times. Okay, so after you do this 5 times, and you can sort of see this happening, you know, we're getting sort of a cycling around of the original sides and angles in this original right triangle. Things are cycling around. Eventually, everything comes back where A, B, C capital are the angles, and side little a, b, and c are the sides. Okay, and it happens on the fifth one. And not only is the fifth one the same, congruent to the original triangle, and it has the same sides and angles, it actually is the same triangle. Okay, so not only do the sides and angles match up, but geometrically, as you go through this process, the fifth one comes around and actually ends up at the same place. And we get this interesting so-called pentagramma mirificum, miraculous pentagram. I believe that Napier discovered this in his works on spherical geometry, trigonometry back in the 1600s, although he did not coin this name. I think this name is something that has come up over the centuries. So this is a really surprising accident of spherical geometry. How, and where does the 5 come from? It's kind of an interesting, it's an interesting theorem. And so that is the theorem I want to prove, that actually when you go around and do this 5 times, you actually come back to the original triangle and you get this pentagram. All right, so there are various ways of doing this. There are straight geometric ways of proving this, which involves some, insight and trickery. It's nothing really terribly difficult, but it certainly is not an obvious theorem. Although I think we would all assume that at some point, this process would have to end somehow. But the fact that you end up at the exact same triangle is a little weird. All right, so what I want to do is show how to use quaternions to do this. All right, and so the tools for this are, first of all, remember an important property of complex numbers, that if you have 2 complex numbers of the same absolute value with an angle theta in between them, then you can map one to the other by multiplying by e to the I theta, cos theta plus I sine theta. Okay, so angle theta in between a and b equals a e to the I theta. In the context I'm going to be looking at, I'm going to multiply by the inverse of a and see this as a statement that b times the inverse of a is equal to e to the I theta. And that's true, of course, for any pair a and b around the unit circle, which have angle theta between them in the counterclockwise direction. Well, I want to generalize that to 3 dimensions, all right, using quaternions. And so most of this, I think everybody is familiar with the basic properties of quaternions. We've seen them in earlier talks today. But the main thing that is a little bit different here is that I'm going to be focusing a lot on the so-called pure quaternions, which have real part 0. Okay, so AI plus BJ plus CK is a pure quaternion. Okay, if there's no real part up front. And the fact is, something like that corresponds to a vector. In fact, sometimes they'll just call it a vector in R3. The fact is, this is where the IJK notation originally came from for vectors in R3. Okay, it originally arose out of quaternions. And the thing that makes the connection to 3 dimensions, even though quaternions are a 4-dimensional algebra, the connection to 3 dimensions arises when you multiply a pair of these pure quaternions. Okay. R1, R2, you've got a sum of 3 times the sum of 3, so you get 9 terms. And when you multiply them out, the II, JJ, and K terms give you minus X1, X2, Y1, Y2, and Z1, Z2. And the cross terms, when you multiply IJ and JI, produce the K term, and IK times KI produces the J term, and the JK and KJ term produces the I term, using the fact that, of course, IJ is K and minus JI is K. I have to adjust some signs a little bit. But if you look at this, then you'll notice that the real part of the quaternion project is minus the dot product, and the imaginary part, or the vector part, is a cross product. Okay, so this really is the connection between a quaternion product and the vector products that we see in calculus. And it is the answer to the question that, if you ever get it in multivariable calculus, why are there 2 vector products? And the answer is there's only one, but the dot and the cross product are simply the components of the quaternion product. All right, so what we're going to do is look at a pair of vectors, say unit vectors in space A and B, and suppose we have an angle theta in between them. And it turns out that if you consider the plane containing A and B, and then the vector E, which is perpendicular to those two, E is really just the cross product of A and B, the vector pointing perpendicular to both A and B. Then it turns out that if you divide B and A, BA inverse, as quaternions, then the quotient is cosine theta plus sine theta E, where E is this vector and theta is the angle between A and B. And that is true for even if you rotate the A and the B around this circle on this plane perpendicular to E. Okay, if the angle between this pair A and B is theta, then this quotient BA inverse is always cos theta plus sine theta E. And so this thing sort of corresponds to the E to the I theta in the complex plane. All right, the proof of this is quite simple. I'm not going to run through all the details of it, but when you look at cosine theta plus sine theta E, the fact is that the cosine theta is associated with the dot product of A and B, and I'm just going to assume they're both of unit length, so it is the dot product. And then E sine theta is the cross product. All right, so cos theta plus E sine theta is A dot B plus A cross B. And then if you just fiddle around a little bit with signs, this becomes minus B times minus A, and you switch the A cross B to B cross A. And then use the fact that the negative of a pure quaternion is its inverse. Then you get the result that this is just minus B dot A inverse plus B cross A inverse, and that's the quaternion product, BA inverse. Okay, so I'm going to use this fact in thinking about what's going on in spherical geometry. The fact is that this gives us a way to associate a quaternion with a directed arc. Directed arcs in vectors in space are things that we understand to have direction and magnitude, but not position. Well, in the same way, a directed arc in the sphere is something that has magnitude and direction, but no position in the sense that you can roll it around a great circle in which it sits. So this V and this W, which I've drawn, they are vectors that I can roll around the great circles in which they sit. And each of them, by what we've seen, by taking the endpoint and dividing, if the endpoint, say, for V over here is B and A is the starting point, then BA inverse is a quaternion associated with that. And it doesn't matter what the position of the red arc is on that great circle. And the fact is, this makes the algebraic structure of adding two such vectors together easy, because if the red vector V is rolled around so that its endpoint is where rolling around W to where its starting point is, then V has quaternion BA inverse and W has quaternion CB inverse. And when you multiply those two together, the B inverse B cancels and you get CA inverse, which is a quaternion associated with a vector that starts out at A and ends up at C. Okay, so there's a direct correspondence between adding vectors and multiplying the quaternions associated with them. All right, one thing I'm going to need in proving the theorem is this little fact that if you have two perpendicular vectors in R3, P and Q, and you multiply PQP as quaternions, that you get Q. And the reason for this is just simple algebra. PQP, if you write PQ as minus P dot Q plus P cross Q, then of course, since P and Q are perpendicular, P dot Q drops out. P cross Q is R, which is this vector pointing up perpendicular to both. But then R times P, all of these being unit vectors, R times P gives you R cross P because the dot product is 0, and so that gives you Q. Okay, so two perpendicular vectors P and Q. If you do PQP, you get the Q. All right, so we'll need that in what arises. So I'm wondering now, in this situation where I have this, start out with this triangle and create all these complemental triangles and all these extra points, you know, how do I get these extra points in terms of the ones that I started with? And what we'll do is use the quaternion associated with each of these directed line segments. So for example, if you look at F and C, okay, the original design was that I extended CB up to F to make that a quarter circle. And what I'm going to do is look at the directed arc from C to F, which has quaternion FC inverse. Well, that has the form cosine theta plus E sine theta, where E is the vector perpendicular to the circle containing C and F. That turns out to be the point I over here. Okay, that comes up sort of later in the construction, but I arose out of drawing a perpendicular from the circle, which is on C and F, and extending that out a quarter circle distance as well. So that makes I the pole, so-called, of the circle CFG. Okay, well, then FC inverse is cosine pi halves, since the length of this FC is pi halves, plus sine pi halves times the E being I. But cosine pi halves is 0, sine pi halves is 1. So this is just I. All right, so seen as quaternions, if I take F, C inverse, I get I. All right, and then multiplying by C in both sides, I can write that as F equals IC. Well, what I'm going to do is repeat this 10 times, basically, for lots of sides that arise in all these triangles, okay? And I won't go through them all in detail, but if you look, for example, at AB extended to be a quarter circle to D, well, look at DA inverse. That's what this directed arc from A to D does, all right? It has pole at H, and so DA inverse, using the same reasoning I did in the previous page, is going to be that pole H. All right, with G and B, B, in the second construction of a complemental triangle, I extended B past F out to G, so GB, that's a quarter circle, and so GB inverse is going to be its pole, which is I, as we saw earlier. And then just one more, HD, H is here, D is here. In the second construction of a complemental triangle, I extended D through F out to H, so that that's a quarter circle. And then HD inverse is equal to its pole, which is A. All right, so you do this a whole bunch of times. All right, multiply by the, DA inverse equals H, multiply by A there, B there, D there, etc., until you get 10 of these equations, which relates the quaternion pointing to each of these points on the sphere. And then getting the theorem is just a matter of doing algebra on all these 10 equations, where our goal will be to show that KMN is actually equal to ABC. And the way that works out is, okay, KMN is to equal ABC. I'll look down at, for example, K. K equals FJ, but up earlier, J was equal to AF. So I substitute this J equals AF down here, and I get F, AF. Oh, but then I have something of the form PQP of perpendicular vectors, and so the FAF is equal to the A, and that gives me K equals A. With M down here is HL, and L up earlier we found is equal to BH, so M is HL, which is HBH, and you get another PQP construction. HBH gives you the thing in the middle, which is B. Now, I do have to check that B and H are perpendicular, but they are. You can look at the picture. And then lastly, with N is Fi, and I, and F up above was equal to IC, so I get ICI, another PQP construction where I get the vector in the middle, and that's C. So KMN is ABC. And that is the quaternion proof of the existence of the pentagramma mirificum. So anyway, I feature this in my book, which came out last year, which I kind of designed for an undergraduate course in axiomatic spherical geometry. And you can get it at the CRC Press website with this discount if you happen to be an MAA member. All right, I'll stop here and thank you.
This is really beautiful. Thank you very, very much. I really love the use of the spherical geometry. I know Rodriguez actually approached his particular way using Pythagorean theorem and spherical geometry, and he actually used half angles, but it was sort of reminiscent what you were doing to some things that I had been thinking about. Thank you for that great talk. Does anybody have any questions?
I've got one.
Yeah.
So you've proved that the first and last triangles are congruent. Have you actually proved that they're identical?
Yeah. So when I showed, I have KMN. These are statements about vectors. So so a point of confusion. I'm using A in two ways here. So when all these letters, these are all pure quaternions and vectors. So when I wrote that K equals A, or K equals Fj, that's a statement of a product of quaternions. And so K equals A then is a statement about two quaternions actually being equal. So the K here is actually the same point as the A. All right. I apologize for double usage of the letters.
So as the last speaker late in the day, at least for those of you in other parts of the country, I'm in Oregon, which is a little different. I'd like to share with you the recent work of an undergraduate student of mine, Isabella Johnson, jointly with my wife, Corinne Minogue, and myself, on presenting quaternionic multiplication visually, and then using that visual presentation to verify some well-known properties of some elementary Lie algebras that in fact are quite useful in a wide variety of applications. So again, this is based on Isabella Johnson's senior thesis. This was a degree requirement for her Bachelor of Science in Physics degree, and you can actually track down her thesis on the OSU public repository, which if you can't find it, drop me a note and I'll point you to it. All right, so here we go. The motivation is that rotations are the key ingredient in the orthogonal groups, which lead to Clifford algebras. Clifford algebras, of course, have applications all over the place. My own interest comes largely from quantum physics, where they provide the mathematical framework for the gamma matrices of quantum mechanics. And again, as we all know in this group, there's a very close relationship between many of the Clifford algebras and the quaternions. But orthogonal groups are not the ones that show up in a lot of applications. It's the unitary groups, which in some sense can be thought of as complex rotation groups. And in fact, all of the symmetry groups, all of the simple Lie algebras can be classified. This is the famous Killing-Cartan classification of simple Lie algebras as rotation groups over one of the division algebras, the reals, the complexes, the quaternions, and the octonions. So we're not going to get that far. We'll see the quaternions at the end of today's talk, not the octonions today. But the motivation is to use this visual representation to talk about rotations in orthogonal and unitary groups as a tool for understanding and analyzing Lie algebras. That's where we're going. All right. So let's start right off the bat with about the simplest one you can have, which is the rotations in 3 dimensions. You see here a basis for the rotation matrices, standard rotation matrices in the Lie algebra of SO3. So these are the infinitesimal versions of the rotation matrices. Think of writing the ones you may be more familiar with sines and cosines in them, and differentiating them with respect to the angle and setting the angle equal to 0. So these are the infinitesimal rotations about the 3 axes. And the visual representation is very simple. It's shown in each case below the matrix to which it corresponds, and just tells you which axis or axes are being rotated with a choice of orientation. And so you can see from looking at the matrix R sub x, for instance, that it involves the y and z directions, only the YZ plane. And it's just a matter of picking a convention. Is this rotating Y into Z, or is it rotating Z into Y? And once you pick that convention, use it consistently. So of course, these are cyclic. An X, a rotation about the X-axis rotates Y into Z, and so forth. And all we're going to do is take these simple pictures and use them over and over again. So Lie algebras, I have to be able to compose the elements in my matrix Lie algebras, so I can build up the Lie bracket by first doing multiplication and subtracting, because I am using matrix Lie algebras at the moment. And the only thing you have to realize is that when I write a product such as Ry times Rx, you work from the right. And so it means do Rx first and then Ry. And so you have to follow, here's Rx on the right and Ry on the left. And so Y drops down to Z, goes to X. And so you can see that rotation, that combination of rotations, Rx followed by Ry, can be constructed by putting these two pictures together and yields Z going to X. Okay. If you now construct the opposite order, you wind up getting X going to Y. Okay. And if you now put those two things together, you get both pieces. Remember, this single arrow corresponded to both a 1 and a -1 in the matrix. It's not just X goes to Y, it's X goes to Y and Y goes to -X. And here we've got those two things with the conventions we're using. I'm reading it with the signs backwards. Unfortunately, I apologize for that. But here's what's being represented as X goes to Y. And here's what's being represented as Y goes to -X. There's a funny sign convention buried in the definition of the arrow. Okay, so we've got Lie brackets. To move on to something a little more complicated. SU2, unitary group acting on two component complex vectors. And I can think of those elements of C2 as elements of R4. So I'm looking separately at the real and imaginary parts. So I have what amounts to a four-dimensional real space. And here visually are those four components, those 4 degrees of freedom. The infinitesimal elements, rotations, if you will, of SU2 are shown here. And all you have to do is track through what Sx does to each of alpha, beta, gamma, and delta. And I've color-coded it. You'll see that Sx will take gamma to alpha and delta to beta, where again, there's that minus sign built into the arrows. And similarly, the green matrix Sy will move you vertically, and the blue matrix Sz will move you horizontally. Notice the opposite orientations in the top arrow and the bottom arrow. So there in one picture is a visual representation of the Lie algebra SU2 as 3 pairwise rotations. And that's the crucial algebraic fact that underlies this representation. SU2, what does it do? It mixes up pairs of alpha, beta, gamma, and delta. You can mix alpha and beta, but also gamma and delta, or you can mix diagonally, or you can mix vertically, but you're always rotating 2 planes at a time. All right. Now ready to start proving results, or at least verifying results. The first one is that we can construct the commutators, the Lie brackets, in SU2, and not surprisingly, verify that even though the elements of SU2 look like they're doing very different things, the commutators, the structure constants, if you will, the Lie algebras are isomorphic. They have the same structure constants. This box showing the 3 Lie brackets is the same as the one I showed a couple slides ago for SO3. So we have verified, not by computation not by algebraic computation, but by visual computation, that these two Lie algebras are isomorphic. All right, now for something more interesting. Let's look at SO4. SO4 consists of the rotations in 4 dimensions. It has a basis rotating any plane you wish. So 4 choose 2 is 6. There are 6 basis elements of the Lie algebra. And if you look carefully, you'll see that the first 3 elements, the T's here, match perfectly with my SO3 basis before, with the addition of a 4th element here called H, a 4th direction that just goes along for the ride and isn't touched by the SO3 subalgebra that's sitting here in the first 3 elements. Whereas the last 3 elements are the 3 rotations that involve the 4th direction with the 1st, 2nd, or 3rd element of the original 3. So that's a choice of basis. There are many bases, of course. So there's a basis. Let me pick a different basis, which is the sum and difference of the basis we had before. So all I'm doing, if I go back to this page before, is I'm going to combine this first operation in the first column with its dual in the 4th column that rotates the other 2 things. And so I get the picture here, which is either the sum, 1st column, or difference, 4th column, of the rotations, one on F and G, the other on E and H, but with opposite relative orientations. Okay, so there's a new basis for SO4. That basis makes it easy to verify the fact that SU2 is sitting there. These pictures that I just showed should look exactly like the pictures we had for SU2. All you have to do is rearrange the dots. And again, they're color-coded so that they match up perfectly. But the top row shows 3 of our new basis vectors for SO4. The bottom row shows the construction we had a few slides back for SU2. And the 2 rows are exactly the same. It's just that the topology of the dots, or not the topology, but the placement of the dots is slightly different. And of course, the other 3 also make a copy of SU2. All that happens as I go back and forth is that some of the arrows change their orientation, and it happens both in the SU2 picture and in the SO4 picture. So what we've really shown, and this is the punchline of what we've done, or what Isabella did in her thesis, was to verify, in fact, the well-known statement that SO4 is precisely, as a Lie algebra, the direct sum of 2 copies of SU2, shown here slightly separated on the left and on the right. Nothing at all new, nice to see visually, and of course something that extends to other Lie algebras. All right, I promised you quaternions. I don't need to remind this audience what a quaternion is, but I do wish to point out that quaternions have, again, 4 real degrees of freedom, which I could think of not merely as H1, but also as R4, or today, C2. Well, C2 looks exactly like what we were doing a minute ago with SU2, and that's why I chose that representation. Quaternionic multiplication by a unit quaternion, of course, just rearranges the things that I've got. And so quaternionic multiplication by units gives me elements of SO4. And the question is which one? And again, this audience likely knows already that left and right multiplication by I, J, and K, so right multiplication shown in the top row, left multiplication shown in the bottom row, mixes up the 4 real degrees of freedom thought of as making up the components of 2 complex degrees of freedom, mixes up those 4 degrees of freedom in precisely the same 6 ways that our SU2 right and SU2 left did a moment ago. The 2 SU2s in SO4 are, again, well-known results, precisely left and right multiplication by unit quaternions. Okay. That's really all I've got to show you. I reiterate that there is no new content in what I'm showing you today, just pretty pictures, but pretty pictures that certainly were new to me. First of all, a visual proof that SO4 does decompose into the 2 copies of SU2. Second, that the left and right correspond precisely to quaternionic multiplication on the left and the right. And my own motivation that SU2 left and SU2 right language looks a lot like the fact that there's an SU2 left in the standard model of particle physics, where you have a chiral asymmetry between the spinors that you have. So you have right-handed and left-handed electrons, say, and the SU2 symmetry of the weak interaction acts only on the left-handed electrons, but not on the right-handed. The algebra, the Lie algebras used to make those statements are precisely these 2 SU2s sitting inside SO4. So the original motivation from me to Isabella to go down this path came from wanting to apply this language, both the quaternionic version and the visual version, to applications to particle physics. And of course, it would not be that difficult to extend these to other Lie algebras. All right, that's all I've got. I thank you very much for your attention. I would welcome questions.
This is really, really excellent. I mean, I like the pretty pictures too. I agree with you. Seeing those pretty pictures really, really did it for me.
Did you give any thought to extending this to my favorite Lie algebra SO13?
So there's not a whole lot of difference for SO13. Again, my pictures are showing 4 real degrees of freedom. But what you now have to pay attention to is the difference between boosts and rotations. And so all of the matrices that I showed you at the beginning were anti-Hermitian or anti-symmetric. And if you suddenly start talking about non-compact groups, so the Lie algebras corresponding to non-compact groups, you can no longer make that anti-hermiticity assumption. So you need a convention in your arrows that tells you that, you know, alpha would be a time-like component and beta, gamma, delta would be a space-like component, and what you mean by reversing an arrow and which signs change and which signs don't. With that change, it should go through in a signature-independent way.
Oh, thanks.
Any more questions?
One more question. Actually,
Sure.
not a question, it's a comment. This picture, it's very close to a picture which I obtained recently in endocrine system, trying to explain endocrine regulation using new type of hormones which recently were found and investigated. And it's very close, but I use split quaternion structures, not quaternionic structures. And actually, I see I'm not surprised, but these 2 structures pretty close in case of some possible symmetries which could be created, but in a problem specific way.
So I hope you are aware, and Itai also, I hope you are aware that the 2 questions you both just asked are almost the same, because using the split quaternions amounts to changing the signature. In Itai's case, it was signature 3-1 or 1-3, and Gary, in your case, it's signature 2-2.
Yes, signature, yes, but it's a different space. Actually, it's a little bit differently working. But anyway, I mean just it's yesterday in my presentation, if Chris, as you remember, and Johannes, I modified a little bit in order to be more understandable for biologists and whatever, biologists and genetics. But from mathematical point of view, this picture very close to that, and I was long time working on it, and it's interesting that it's it may be some kind of not coincident but in parallel ways leading to the close things. Thank you.
Yeah, my understanding, of course, was through physics and the spin matrices. And when you mentioned about boosts and everything, I go, yes, right, yep. I knew that from, or that's where I recognized it from. Thank you very much. Any other questions out there?
Yeah, should we put a plug in for our webpage?
Yeah, we can put it. You have it up behind you. I think you're in a better position than I am right now.
Okay, so. All right, can you see the, are you seeing the website?
Yes, I am.
Okay, so everyone's invited to come
iPad
to
and my Surface.
And we post news about quaternions, and we have videos of presentations that were done at previous conferences. And so after this conference, you'll probably get an email from us requesting any material that you would like to post. And we'll put it online for you so you can share it with a wider audience if you're interested in doing that.
Yeah, it's all OER, purely OER.
Yeah.
Open education.
It's easy to find this. If you Google it, it's the first one that will come up. All right. And thank you everyone for coming to our session. You really made it
well, that's what makes the sessions great. It's the people who attend, the organizers. We just organize. Anybody have any questions, comments, or anything?
I just want to offer the following comment. If any of you have not seen the music video William Rowan Hamilton, just search for it on YouTube. It's hilarious.
Oh, I'd love to. Thank you. Thank you for that plug-in. Maybe we'll put the link after we look at. We'll put the link on our Quaternions Notices.
Yeah, it's great.
Yeah, thank you for that.